Now students, let us see domain and range of a relation. For that, I will begin with the pictorial form of a relation to understand in a better way. So consider a relation in which the first set is A and the second set is B. First set has elements A, B, C, D. Suppose second set has elements 1, 2, 3, 4, 5. Now in this case, suppose A is related to 1, B is with 2, B is with 3 and D is with 4. If this is the situation, and this is the kind of relation. R is a relation from set A to set B. In this case, in this relation, if I make out the pair of elements in the relation, so in the pairs will be A1, B2, B3 and D4. So these are the pair of elements in the relation. So this is the relation in the ordered pair form, and this in the pictorial form. The definition of domain is set of all first components in the relation. If this is the relation, then set of all first component means A, B and D. C is not involved in the relation, although it is there in the first set. So C is not involved in the relation. So in this case, domain will be set of all first components. So domain of R, set of all first components such that the ordered pair belongs to the relation. And similarly, range of R, set of all second components such that the ordered pair belongs to the relation. See, in this way we can define the domain and range of a relation. In a classical manner, the same can be shown like this. So this is domain of R, set of all first components X such that XY belongs to R, and range of R is set of all Y such that XY belongs to R. So here X means that X is the first components, Y means the second components. Now if we use this relation, we use this definition to this relation as I have shown here, domain of the relation is ABD, and range of the relation is 1, 2, 3 and 4. Also we can observe that in this case the domain of R is a subset of A and range of the relation is a subset of B. Now say relation on a set. When can we say R is the relation on a set A? Generally we say relation from set A to set B. Then when can we say that R is a relation on A? Let us say this. So if R is a relation from set A to set A, that means first set and the second set elements are the same. So this is also A and this is also A. 1, 2, 3 and 1, 2, 3 here. And if this is the relation. So if in this case, if the domain and codomain both are the same set, then we say that R is a relation on A. Rather than saying R is a relation from A to A, we directly say this, R is a relation on A. So that is about relation on a set. Now see inverse of relation. Suppose R is a relation from set A to set B. Then a relation defined from set B to set A is called inverse of the relation. Inverse of relation R, it is denoted by R inverse, R to the power minus 1. This is the notation for inverse of relation. So if R is from A to B, then inverse of relation R is from B to A. Pictorial form of the same is if A is the set, first set, B is the second set, R is from A to B, relation R is from A to B, and then R inverse relation will be from B to A. So this is the situation. So if R is the relation from A to B, the inverse relation R inverse will be from B to A. So what will be the classical definition of inverse relation? So R inverse is the set of all B comma A such that A comma B belongs to R. So this is the actual relation and this is the inverse. In this case, you can notice that the domain of the relation R has become the codomain of R inverse, and codomain of R inverse has become, codomain of R has become domain of R inverse. So this you can see a kind of interchanged in domain and codomain, and in the same time range also. Okay, so this is about inverse relation. Let us see example on this. Consider this example, students. In this case, A is the set having elements 1 to 3, B, P, Q, R, S, and this is the relation you can see. Then what will be domain and range of inverse relation? What will be inverse relation? So in this case, since R is this, so R inverse, the inverse relation will be P1, P2, Q2 and S2. Okay, we have reversed the corresponding elements. In this case, what will be domain of R inverse? So domain of R inverse is P, Q and S. And what will be range of R inverse? Range of R inverse will be set of all second components 1, 2, that's all. So this is about domain of inverse relation R and range of inverse relation R. Very simple. Now see the second example. In this example, the relation R is defined on A, and the set A is given to be set of all natural numbers having elements 1, 2, 3, 4, 5, 6, 7, 8, 9. We have to find out relation R, domain of R, inverse relation and its range. See in this case, what is the condition for the relation? The condition for the relation is x plus 2y is equal to 10. This means 2y is equal to 10 minus x, and this means y is equal to 10 minus x by 2. So referring this, we are going to find the pair of elements for the relation. So let us do one by one. When x is 1, then what is y is equal to? Put x equal to 1 here. So 10 minus 1, 9 by 2. So y is 9 by 2. But see that 9 by 2 is not from the set A. That means y cannot be the second component of the relation. This does not belong to A. Okay? That's why this pair is not valid. For x is equal to 2 does not belong to A, and therefore this 1 comma 9 by 2, this does not belong to the relation. This is our conclusion. Now for x equal to 2, 10 minus 2 is 8. 8 by 2 is 4. So y is 4. For x equal to 3, 10 minus 3 is 7. 7 by 2, y is 7 by 2. So this does not belong to the relation, again due to the same reason that 7 by 2 is not from A. Then x equal to 4. For 4, 10 minus 4 is 6, 6 by 2 is 3, so y equal to 3. Then x equal to 5, y is equal to 10 minus 5, 5 by 2. Again, this does not belong to the relation because 5 by 2 is not in A. Then x equal to 6, so y equal to 10 minus 6, 4. 4 by 2 is 2. And x equal to 7, y equal to 10 minus 7, 3 by 2. This also does not belong to the relation. X equal to 8, y is equal to 10 minus 8 is 2, 2 by 2 is 1. X equal to 9, y is equal to 10 minus 9, 1, 1 by 2. So this does not belong to A, so this does not belong to the relation. X equal to 10, y is equal to 10 minus 10 is 0, 0 by 2 is 0. So 0 is also not in A, so this also does not belong to the relation. So let us see which are the elements which follow the relations. So I will tick those, this 1, 2, 3, 4, that's all. So the relation is the set containing pairs. I will choose this one, 2, 4. Then second tick this one, 4, 3. And next one is 6, 2. Next one is 8, 1. That's all. All other pairs corresponding to x equal to 1, 3, 5, 7, 9 and 10 does not satisfy the given condition. So these are the pairs in the relation. So this is the relation. So answer to the first segment. Then domain of R. So domain of R means set of all first components. That means this is 2, 4, 6 and 8. This is domain of R. Next is R inverse. R inverse, in R inverse we have to just reverse the elements in R. So R inverse will be 4, 2, 3, 4, 2, 6 and 1, 8. This is simply the R inverse relation. And then we have to find out the range of R inverse. Range means set of all the second component in the relation. So range of R inverse will be set of all second components, means 2, 4, 6 and 8. 2, 4, 6 and 8. That's all. So this was very important to understand relation, its inverse, and how to use the given condition in relation. Okay. Now let us solve some examples based on relations. So first example, A is given to be a set having elements 1, 2, 3, the set B having 4, 5, 6. Then we have to decide which of the following relations from A to B, which of the following are the relations from A to B, and give reasons. So first one is relation R1, 1 having elements pairs 1, 4, 1, 5, 1, 6. Okay. So which of the following are relations that we have to decide. The first one we have chosen. So let us see the answer. So in this, if we check 1, 4, whether 1 is from set A or not, 4 is from set B or not. Right, 1 is from set A very well, 4 is from B, 1 is from A, 5 is from B, 1 is from A, 6 is from B. So everything is right here. That means R1 is a subset of A cross B. So here 1, 1 belongs to the set A and 4, 5, 6 belongs to set B, and that's why this R1 is a subset of A cross B, and therefore R1 is a relation. Right, first segment means that is only 1 here. 1 is from the set A, 4, 5, 6 these elements are from the set B. That means these pairs are formed from A cross B. So R1 is a subset of A cross B, and hence R1 is a relation. Second one now, R2 1, 5, 2, 3 and 3, 6. You check the elements or the pairs here. Here 1 is from set A, 5 is from set B. Okay, first pair is from A cross B. 2 comma 3. Now 2 is from A. 3 is also from A. Ideally 3 should have been from the set B, but here 3 is from A. 2 is also from A. 3 is also from A. That means 2 comma 3 is not from A cross B. Due to this pair, this R2 cannot be a relation. So we will mention here कि 2 comma 3 belongs to A. Therefore R2 is not a subset of A cross B. That's why R2 is not a relation. Okay, so as I explained earlier, this 2 is from A, but 3 should have been from B, but 3 is from A again. That's why this pair 2 3 is not from A cross B, and hence the relation R2 is not a subset of A cross B, and hence this is not a relation. Now R3 here, R3 having 1 4 1 5 3 6 2 6 3 4. You can check 1 is from A, 3 is from A, 2 is also from A, 3 is also from A. So at the first position, whatever elements are given here, all are from the set A. Now second position, 4 is from B, 5 is from B, 6 is also from B, 4 is also from B. So strictly first position elements are from the set A, and the second position elements are from the set B. So ideally R3 is a subset of A cross B. So 1 3 2 belongs to A, and 4 5 6 belongs to B, and therefore R3 is a subset of A cross B, and therefore R3 is a relation from set A to B. This is the answer and the justification. Now the fourth one, R4, these are the pairs. So we'll check that the first position elements 4 2 5. 4 is from second set B, 4 is from second set, 2 is from first set, 5 is from second set. So there is a contradiction. So 4 comma 5 belongs to B, and at the second place we have 2. So 2 1 belongs to A. This is a wrong thing here, and that's why R4 is not a subset of A cross B. Okay, first place elements should be from A, but here first place elements 4 and 5 are given from B. This is wrong. So that's why R2 is not a subset of A cross B, and that's why R4 is not a relation. From A to B. That's all for the first question. Now see the second question. A relation R is defined from set A to set B. It is defined like X divides Y type, X comma Y when X divides Y. So we have to find out the relation R and its domain and range. So how to find, you see? First of all, one by one we'll see 2 divides which element of B? 2 divides 3? No. 2 divides 6. So here I will write 2 divides 6. Then 2 divides 10. And that's why this 2 comma 6, 2 comma 10, these are the pairs in the relation. Okay, that's all from 2. Now go to the second element 3. 3 divides 3. Now 3 divides 3. Then 3 divides 6. 3 divides 7 not possible. 3 divides 10 not possible. And so 3 3 and 3, 6. These are the elements belonging to the relation R. Then go to next element 4. 4 divides 3 is not true. 4 divides 6, 4 divides 7, 4 divides 10, not possible. So we cannot make out any pair. Then 5 divides 3, no. 5 divides 6, no. 5 divides 7, no. 5 divides 10, also 5 divides 10, and that's why 5, 10 is the another pair from the relation. So these are the pairs in the relation. These are the pairs, and this is the last one. So what will be the relation then? Let us see. Therefore relation R will be having pairs 2, 6, 2, 10, 3, 3, 3, 6, and lastly 5, 10. Okay, so this is the relation finally, satisfying the condition x divides y, that means first element divides second element. You can cross check. 2 divides 6, okay. 2 divides 10, okay. 3 divides 3, okay. 3 divides 6, 5 divides 10, okay. So all are correctly paired. Now we have to find out the domain and range. So domain means collection of first elements. So domain of R is the set of all first components 2, 3, 5. So this is the domain of R. And then range. So range of R, this is the set of all second components. So 6, 10, 3, 6, 10, 3, 6, that means 3, 6 and 10. Writing in a proper serial. That's all. So under the given description of a relation, we have found these pairs. So relation R is having these pairs and has domain 2, 3, 5 and range 3, 6, 10. Now in the next question, we have to find out a relation R which is defined on the set Z in set of all integers, satisfying this important condition. So we have to choose the ordered pairs x, y in such a way that x square plus y square is 25. So let us begin the solution. So given x square plus y square is 25, this will mean y square is 25 minus x square. So we get y is equal to plus minus root of 25 minus x square. So this is that condition which we have to satisfy indirectly. So let us choose the values of x as 0, plus minus 1, plus minus 2, plus minus 3, etc. And let us see find out the values of y. So first of all, if x is equal to 0, then what will happen? 25 minus 0 is 25. This is a perfect square. So this will go plus minus 5. Value of y to be plus or minus 5. That's why the pair of elements are 0, plus or minus 5. Okay, actually there are two values 0, 5 and 0, minus 5. Next to this we will choose x is equal to plus or minus 1. Since there is x square, we are choosing plus or minus. So what will be y then? Is it possible to find out y? If we put 1 here, so 1 square is 1, 25 minus 1 is 24. 24 is not a perfect square. So since 25 is not a perfect square, finding value of y is not possible because y has to be integer. Okay, so y is not possible. What will happen? Root 24 is not an integer. That is the reason. So finding y is not possible for x equal to plus or minus 1. Now let us try for 2. 2 square is 4. 25 minus 4 is 21. 21 is again not a perfect square. So again finding value of y as an integer is not possible when x is 1, x is 2. Then for 3, plus or minus 3. For x equal to plus or minus 3, y will be 3 square 9, 25 minus 9 is 16. Root 16 is plus or minus 4. So plus or minus 4 is values of y. This will give the ordered pairs to be plus minus 3 plus minus 4. So there are many, actually 3 minus 4 minus 3 4 minus 3 minus 4 etc. That we'll see later on. So broadly we are finding the pairs. Then x is equal to plus or minus 4. So putting x equal to 4 here, 4 square is 16, 25 minus 16 is 9, again a perfect square. So root 9 is plus minus 3. So y will be plus or minus 3. This gives the pair of elements to be plus or minus 4 comma plus or minus 3. Then for x equal to 5, 5 square is 25, 25 minus 25 is 0, so y will be 0. So x is equal to plus or minus 5, y will be 0 simply. So pair of elements are plus or minus 5 comma 0. Now if we choose the value x equal to 6 onwards, 6 square is 36, so 25 minus 36. So here we will be getting a negative number under the square root. So negative number under square root is not going to give any integer. So taking values of x equal to 6 onwards is not possible. So these are the only values possible for x, and these are the only pairs. So which are the actual pairs? If we write everything in detail, then which are the actual pairs? Let us see here. So R will be like this. So this is R. 0 plus minus 5 gives 0 5 0 minus 5 plus 3 plus minus 3 plus minus 4 gives 1 2 3 4 pairs. Then plus minus 4 plus minus 3 gives these 4 pairs, and plus minus 5 0 gives 5 0 and minus 5 0. And if this is R, then reversing the position of the elements in the ordered pairs, we get R inverse like this. Okay, this is 0 5, then 5 0, 0 minus 5, then minus 5 0. In this way we can write R inverse. So in this way these are the relations R and inverse relation R. Now we have to find out their domains. So domain of R is set of all first components. So we can take 0, 3, minus 3, 4, minus 4, 5 and minus 5. And domain of R inverse, that will be 5, minus 5, 4, minus 4, 3, minus 3 and 0. So these are the domain of R and R inverse. Now observing domain of R and domain of R inverse, we can easily see that so 0 is also there, 3 is also there, minus 3 is also there, 4 is also there. In fact, all the elements in domain R are in the domain of R inverse also. So what is our conclusion? So from here we can write domain of R is equal to domain of R inverse. That's all. Now next question, let A is having elements 1 2 3 4 5 6 and relation R is defined on set A. Defined on A means the first component x should be chosen from A and the second component y also should be chosen from A only, and satisfying this relation y is equal to x plus 1. Now these are the questions which we have to answer, students. So let us begin with the answer. So first one, express this relation using an arrow diagram. Now initially mind this relation given y is equal to x plus 1. So let us put x equal to 1, then 2, then 3 and find out corresponding value of y. So when x is equal to 1, y is equal to 1 plus 1, 2. X is equal to 2, y is equal to 2 plus 1, 3. X equal to 3, y is equal to 3 plus 1, 4. X equal to 4, y is equal to 5. X equal to 5, y is equal to 6. And x equal to 7, x equal to 6, y is equal to 7. See this situation. When the value of x is 6, value of y comes up to be 7. This is not possible because this value also should be from the set A only. 7 is not there in A, so this value is not possible. So x equal to 6, y equal to 7 pair is not possible. So which are the pairs then? This implies 1, 2, 2, 3. This implies 3, 4. This implies 4, 5. This implies 5, 6. This is not the pair. So how to depict this relation? These are the pairs in the relation, right? So these pairs are to be shown in the form of diagram. So the actual relation R is having these pairs 1, 2, 2, 3, 3, 4, 4, 5 and 5, 6. And the pictorial diagram of the same relation, if I write R here in between, R is from A to A. So A having 1, 2, 3, 4, 5, 6, A having 1, 2, 3, 4, 5, 6, but the relations are like 1 to 2, 2 to 3, 3 to 4, 4 to 5 and 5 to 6. In the first set, 6 is not related and here 1 is not related. Okay, so this is the answer of the first question. This is the relation R. Now second question, write down the domain, codomain and range of R. So domain means what? Domain of R, set of all first components. So 1, 2, 3, 4 and 5. 1, 2, 3, 4 and 5. This is the domain of the relation. And then codomain. Codomain of R is the complete set. I will write range first, that will be easier for you. So range of R will be set of all relations. So 2, 3, 4, 5, 6. 2, 3, 4, 5 and 6. Whereas codomain means the complete set 1, 2, 3, 4, 5, 6. You see the difference here in the range. Range means all related elements 2, 3, 4, 5 and 6. 2, 3, 4, 5 and 6. But codomain means complete set 1, 2, 3, 4, 5 and 6. So that's all. In the next question, R is a relation given between P and Q. This is the picture for that relation, diagrammatic representation. In this question we have to express the same relation in the roster form and in the set builder form. So first one, you see the roster form of this. Roster form means actually we have to list the pair of elements in the relation R. So clearly it can be seen 9 is related to 3, 9 to minus 3, 4 to 2, 4 to minus 2, 25 to 5, 25 to minus 5. So therefore required relation R is, you can pair 9 to 3. So 9, 3, 9 minus 3, 4, 2, 4 minus 2, 25, 5 and 25 to minus 5. So this is the required roster form. Roster form of the relation. Now see the second part of this question. In the second part we have to find the set builder form of this relation. So in this, suppose the first set elements represented by X and the second set elements are represented by Y. It is clear that minus 3 square is 9, 3 square is 9. So X is equal to Y square. If we square Y, then we get X. That means x is equal to y square is the relation everywhere. 5 square is 25. 5 square is 25. So that is the relation between the elements. So we can write the set builder form as R is equal to set of all x comma y such that, so what is the relation? Y square is equal to x. Okay, y square is equal to x. So this is the set builder form of the relation. Next we have to write down the domain and range of this. So domain of the relation R is set of all first components, that is 9, 4 and 25, and range of R is set of all second components. See that the element 1 in the set Q is not associated anywhere, so we will not write that. So that will be 5, 3, 2, -2, -3 and -5. So this is the range. In the next example, R is the relation defined on Q, and R is defined as set of all AB such that AB belongs to Q and A minus B belongs to integers Z. So we have to show that A comma A belongs to R and other two segments also. Actually, these kind of examples are very important for your JEE approach. Your development in mathematics begins with such kind of questions. So first what we have to show that A comma A belongs to R. So such a pair also is a part of the relation that we have to show. So we have to see that whether this A comma A, these two elements satisfy this condition and this condition. Yes, A comma A, AB belongs to Q, so A comma A also belongs to Q. So what about the second condition? Here we can see that here A minus A, if we subtract these two elements, A minus A is 0, and definitely 0 is an integer, so 0 belongs to Z. So A minus A belongs to Z, and that's why A comma A belongs to R. Since all the conditions given here are satisfied by these two elements A and A. What? A and A belongs to Q. Okay, because in relation only it is given that A, B belongs to Q, so both the elements belongs to Q, and important is A minus B belongs to Z. So here we subtract first and second elements A minus B, then that gives 0, and that is integer variable. That's why that important condition is satisfied, and that's why A comma A belongs to R. So first part is proved for all A. Now see the second part. We have to show that A comma B belongs to R implies B comma A belongs to R. That means this is the given condition. A comma B already is a member of the relation. So given A comma B belongs to R, this will imply A minus B belongs to Z. Obviously A comma B are from Q. So this is the condition. Since A comma B belongs to the relation, so A minus B belongs to Z according to the given condition in the definition itself. Now since A minus B is an integer, we know that if 7 minus 4 is an integer, if 7 minus 4 is 3 is an integer, so 4 minus 7 is minus 3 is also an integer. So whenever A minus B is an integer, B minus A is also an integer. With the same claim, we can say that A minus B belongs to Z. This implies B minus A also belongs to Z automatically according to this claim. Since B minus A belongs to Z, now the first element is B and the second element is A. That means the pair B comma A belongs to R. Okay, whenever this subtraction belongs to Z, then this pair B comma A, first element comma second element will belong to the relation. So B comma A belongs to R. In this way we have proved that A comma B belongs to R implies B comma A belongs to R. So this is the proof of the second part. Now let us prove the third part of this. In the third part, it is given that A comma B belongs to R and B comma C also belongs to R. We have to show that A comma C belongs to R. Now since these two pairs belongs to R, so by the given condition A minus B belongs to Z and B minus C also belongs to Z by definition. Now I will again give the cross example. If 5 minus 2 is 3 is an integer and 2 minus 7 minus 5 is also an integer. This is an integer, this is an integer. Okay, so if I add these two, this plus this is 3 plus minus 5, this is minus 2, so automatically this is also an integer. So difference between two numbers is an integer, difference between this number minus another number is also an integer, so addition of these two numbers will also be an integer. I have shown it here. 3 plus minus 5 is minus 2 is an integer. So according to this claim, this is an integer, this is an integer, so their addition is also going to be an integer. So therefore A minus B plus B minus C also is an integer. I have added these two, so cancelling B and minus B we get A minus C, so this is also an integer. So A minus C is an integer. Now according to that definition, first number minus second number belongs to Z, that means the pair first number comma second number belongs to the relation. So therefore we get A comma C belongs to the relation. In this way we have started with this pair belongs to R and this pair belongs to R, and we have shown that A comma C belongs to R. Now the next question is R1 is the new relation given on set of all real numbers R, and the definition is like A comma B belongs to R1 equal implies 1 plus A into B greater than 0. 1 plus first number into second number is positive, means first number comma second number belongs to the relation and vice versa. What we have to show that A comma A belongs to R1 for all A belongs to R. So let us prove this. We know that for all A, such a number A belonging to the real numbers, 1 plus A into A. What is 1 plus A into A? That is 1 plus A square. Now for any real number, square is also already a positive number, so this is a positive number plus 1, so this is totally a positive number, so this is greater than 0. So 1 plus A into A is greater than 0, so this is going to be the first number in the pair, this is going to be the second number in the pair, so this implies A comma A belongs to R1 by this definition. We have shown that 1 plus A into B is positive, 1 plus A into B is positive. That's why A comma B belongs to R1. So A comma B belongs to R1. In this way, first part is proved. Now see the second part. In the second part, given that, so given part in the second part is A comma B belongs to R1. So this pair belongs to R1 means for these two numbers 1 plus A into B is positive. This pair belongs to R1 means by definition 1 plus A into B is positive. So therefore I can write, since multiplication is commutative in real numbers, the same statement I can rewrite as 1 plus B into A is also positive. Easily we can write for real numbers. Now 1 plus this number into this number is positive, that means first number comma second number belong to the relation. So we have started with A comma B belongs to R1. This implies B comma A belongs to R1. So that is the proof of the second part.